Good day to all. Today, our group, which is Group 14, will be presenting our finding about the real gas and ideal gas piston.
In chemical engineering, understanding gas expansion and compression is fundamental. These processes govern the design and operation of critical industrial equipment, including power generation system, pipeline networks, and carbon capture facilities. In traditional coursework, we often rely on the ideal gas model because the mathematics are simple and fast. However, as shown under the background points on the screen, the ideal gas model completely breaks down under high pressures or low temperatures. This happens because it incorrectly assumes gas molecules have zero physical volume and no molecular interactions. To bridge this gap safely in real-world design, we looked at the van der Waals equation of state. The primary objective for this project was to design a comprehensive MATLAB simulation tool to bridge this gap, calculating real volumetric changes, quantifying actual boundary work, and automatically generating comparative curves so we can visually isolate exactly where ideal assumption failed. Moving on to the system description, the simulation focuses on a fixed, unreactive gas chart trapped inside a completely frictionless, perfectly sealed piston cylinder assembly. The application evaluates this system through two distinct thermodynamic paths that mirror real industrial environments. First, an isothermal process where temperature remains strictly constant as heat transfers slowly to keep the system in thermal equilibrium. Second, a polytropic process, which acts as a more realistic laboratory model where pressure and volume shift according to expression PV n equal to C. In both scenarios, as the piston moves dynamically between an initial volume and final volume, the boundaries shift. The program tracks this behavior to calculate the exact amount of work done or required, allowing for a direct side-by-side performance check of both models under identical operating constraints. To pull this off mathematically, the methodology evaluates the gas state by tracking the continuous path of each process line over discrete volume increments. To correct the flaws of the ideal gas model, the real gas calculations integrate the two classic van der Waals parameters. Parameter A accounts for the attractive forces between molecules, which pull them away from the container walls and reduce the observed pressure. Parameter B, known as the co-volume, accounts for the actual physical space that the gas molecules occupy. To keep the underlying calculations stable, a few standard engineering assumptions were applied. The cylinder is treated as a perfectly closed system with zero mass leakage. The piston moves under frictionless, quasi-equilibrium conditions. Changes in kinetic or potential energy are considered negligible, and parameters A and B are treated as constants that don't fluctuate with temperature spikes.
Now for the modeling approach, the simulation analyzes how gas state changes during process by comparing ideal gas and real gas behavior. For ideal gas, molecules are assumed to have no volume and no intermolecular forces. For real gas, van der Waals equation, which inputs two parameters, are used, which is A, representing attractive forces between molecules, and B, representing the volume occupied by gas molecule. As the piston moves, the simulation track changes in pressure, compressibility, and volume. Then calculate the work done by the gas throughout the process. In this part, I will explain the coding implementation of our simulation application. The application was developed using MATLAB App Designer, which allows us to build an interactive graphical user interface and organize the program using a class-based structure. This makes the code easier to manage and maintain. The interface includes 5 input fields where user enters the main thermodynamic parameters such as initial pressure, initial volume, final volume, temperature, and polytropic exponent. A run button acts as the main trigger to start the simulation, while two plotting axes display the PV diagram and efficiency graph. When the Run button is clicked, the program reads all input values and performs thermodynamic calculation for both the ideal gas and the real gas model using the van der Waals equation. This allows comparison between ideal and real gas behavior. Before running the simulation, the program performs input validation to ensure all values are valid and physically reasonable. If an error is detected, the simulation stops and an alert message is shown. After validation, the program calculates pressure, changes across multiple volume points, computes the work done during the process, and determines the compressibility factor. Finally, the result and graph are displayed to the user. To improve reliability, the program also uses error handling through a try-catch block, preventing crashes and ensuring a smoother user experience.
Now I will present the results of our simulation. From the generated pressure volume graph, both gases follow the expected trend where pressure decreases as volume increases during expansion. However, the real gas model shows slight deviations from the ideal gas model because it considers intermolecular forces and the finite size of gas molecules. The simulation also calculates the compressibility factor Z. For an ideal gas, the value of Z remains close to 1, while the real gas model shows deviations from 1, indicating non-ideal behavior. In addition, the work done during compression and expansion processes is calculated. The differences in work values between the two models demonstrate the effect of real gas behavior on calculations. Overall, the results show that the van der Waals model provided a more realistic representation of gas behaviors compared to the ideal gas model. Next, I will explain the user interface of the application. The interface is designed to be simple and user-friendly. It consists of 4 main sections: the input panel, control panel, results panel, and graph panel. Users first enter the required thermodynamics parameters such as pressure, volume, temperature, and polytropic exponent in the input section. After entering the values, the user clicks the Run button to start the simulation. The application then performs all calculations automatically. The results panel will display important calculated value, while the graph panel visualizes the simulation outputs, allowing users to compare the behavior of ideal and real gases more easily. This interface enables users to quickly analyze gas processes without needing to manually perform complex calculations. In conclusion, this project successfully developed a MATLAB app designer simulation for analyzing gas behavior in a closed piston cylinder system. The simulator compares the ideal gas and van der Waals model and evaluates their performance during compression and expansion processes. The results demonstrate that real gases can deviate from ideal gas predictions, especially when intermolecular forces and molecular volume become significant. Therefore, the van der Waals equation provides a more realistic representation of actual gas behavior. Overall, this project helps improve understanding of thermodynamic principles and serve as a useful education tool for studying gas processes and real-world engineering applications. Thank you.